I want to talk about a first order circuit, this case being with a capacitor with a bunch of resistors and a driving independent source, and to try to look at how we would think about solving these systems. Now the first thing before we go any further is notice that we have one capacitor, and that capacitor sort of sets the conversation. That capacitor, of course, means I have the one state variable which really sits on this node. We're going to talk about ground being kind of fixed, so it's really going to be related to this node, which is going to be the output voltage. And then the question is, so beyond this capacitor, the question is, what is all of the stuff around here going to do? And so what you're basically left with is a very interesting question. With all these elements, particular values given, what you find is that I need to basically solve what this whole structure is, and I need to ask, what is the effective, say, one-port equivalent, which that could, of this entire circuit, and that could be either a Thevenin equivalent or a Norton equivalent. Because if I can do that, it gets me into an interesting spot. Now you might ask, how would I think about doing a Thevenin or Norton equivalent in this structure? And one way to approach this is that, notice I've got a Thevenin circuit here. If I made that into a Norton, then I'm going to have two resistors here, R1 and R2 in parallel, so I can already combine those together. Move that Norton version back to a Thevenin equivalent, add it with R3, and then again, I just need to then flip it again to do R4, to pull the R4 into there to come up with an equivalent resistance. Well, it turns out that equivalent resistance would be R1 in parallel with R2 plus R3, all of that in parallel with R4. Interesting enough, that would give me a value with these particular values as 5 kilo ohms for my effective resistance. You think, okay, that's cool. Turns out my effective voltage, after doing the Norton Thevenin sort of equivalence, is that each sort of pair of combinations is then going to basically reduce Vin by a half. So the first one, forward and backward, because of the parallel resistors, is going to get it to 1/2. The second one will be 1/4. And so the effective voltage is going to be 1/4 Vn of t. So just this very straightforward Thevenin equivalent circuit, which you may have seen in other videos and other discussions, is basically all that needed to go from here to here. But look at what happens once I have that. Now I have this whole circuit here transforms into what looks like a very straightforward RC circuit. And we can see this in other places, but just to kind of go through it briefly, what you're going to find is you have an effective resistance and effective capacitance. So you definitely can immediately find out your time constant. 5 k ohm times 200 nanofarad gives me 1 millisecond. I also get the resulting differential equation out of this. The tau would show up just as you would expect from solving that equation. And then I also get 1/4 of Vn, because after all, that is what my effective voltage actually looks like. And so in many cases, if one even has a question of like, well, why do I worry about one-port circuits? And there's many reasons to care, but one of the most interesting ones in a case like this is it really helps me really reduce this circuit down into what is a very canonical form that I know and just very quickly can figure out what the results of that look like.